Hello everyone, this is the video for lecture 18, and today we are going to start chapter 14 on sound. We talked a little about sound waves in the last lecture. At the top I just summarized what we talked about, and it's also a little more general in that here, rather than sound requiring air to travel through, here we say that sound can travel through any medium. This GIF here is supposed to illustrate how a tuning fork would create sound in the air. When you strike a tuning fork, the tines of the tuning fork vibrate back and forth very fast. When the tuning fork tine vibrates outward, it creates a high density region that's like a peak of the wave. When the tine vibrates inward, it creates a low density region, which is like a crest. Or for longitudinal waves, we call them compression and rarefaction regions. The second GIF that I just found here at the bottom shows this in action. So the tines vibrate back and forth. As it vibrates to the right, it creates the compression. When it goes left, it creates the rarefaction region. In case you've never seen a tuning fork, I found this video to show you what happens in action. This is very much in slow motion. But as you can see, the tines are vibrating back and forth. What's interesting about this video is that so when the tuning fork normally vibrates, you do not see the waves that it creates in air, of course, because air is completely transparent. But when the tuning fork enters the water in this glass at the bottom, you're going to see waves created by the tuning fork. And these waves are very similar to what's happening in the air. In the center, you can even see some interference of the waves, which is interesting. And these tines are actually vibrating very quickly, so it's disturbing the water quite a bit, and that's what's creating these water droplets that fly out. And then when the droplets start hitting the water, they create even more waves that are interfering with the other waves, and you just have wave interference all over the place. So here's a quick question for you. We know that sound waves can obviously travel through air, but can they also travel through water? What about solids? And also, what about outer space? Now, the answers to these questions may seem fairly obvious to you, but I want you to think about why it's true. Unpause when you're ready. So, sound can certainly travel through water. In fact, it works much the same way as it does in air. Water is a bunch of molecules loosely bound together, so what you see happening in this GIF could also be illustrating sound traveling through water. In fact, this is how animals communicate when they live underwater. Dolphins, whales, they use echolocation to talk to each other. Now, what about solids? The molecules in a solid are also bound together, but they're very tightly bound together. Well, actually, this GIF would still apply. Since the molecules in a solid are tightly bound together, the molecules here may not move left and right as much, but they would still be vibrating. In fact, if you've ever had a neighbor that plays their music too loud, you've seen this in real life or heard this in real life. The sound travels from their speakers through the air. The sound bounces off the wall, causes the wall to vibrate. Then that vibration travels through the wall into the air in your room, which then causes sound to be created in your room, which travels to your ears. Outer space is different though, because in outer space we don't have air or water or a solid in order for sound to travel through. There's no medium in outer space. Therefore, sound cannot travel through outer space. There's no molecules, like in this GIF, to vibrate back and forth that allow sound to travel. There was a famous tagline from this movie Alien in 1979. It said, "In space, no one can hear you scream." that's where the tagline comes from. So if you wanted to soundproof a room, for example, what you could do is create a vacuum between your room, and the outside environment. Then sound could travel, say, from you in the room outward toward the vacuum, and then it would just stop at the vacuum. And there would be no way for that sound to transfer into the outside environment. Audible waves are sound waves that humans can hear, and they typically have frequencies in the range of 20 to 20,000 hertz. So those molecules vibrating back and forth in the GIF, they would be vibrating anywhere between 20 times per second and 20,000 times per second. Infrasonic waves are sound waves that have frequency below the range that humans can hear. So some examples of things that create infrasonic waves are earthquakes, volcanoes, and avalanches. Animals can also produce infrasonic waves. Whales and elephants are a few examples of these. Infrasound actually travels much further than audible sound waves, so animals that use infrasonic waves to communicate can do so with up to hundreds of miles away from each other. Nuclear weapons, of course, create a lot of sound. The highest frequency waves may fizzle out after a few miles, maybe hundreds of miles, I'm not sure. But the infrasound that's created by nuclear weapons can travel much, much further. So the United Nations actually sets up infrasound stations around the globe so that they can detect infrasound that's coming from nuclear weapons. In this way, they can enforce their nuclear test bans. And this next bit is kind of interesting, although I can't really verify it personally, and I haven't really seen many studies on it, but it has been suggested that infrasound can be used to explain ghost sightings or paranormal activities. So if you want to look up the name Vic Tandy, you can read about his story. But from what I understand, he did some research into infrasonic waves. So the story goes that he was sitting in his office and he was seeing weird things. Maybe he saw a ghost out of the corner of his eye. He felt depressed maybe, and he wasn't sure why until one day his fencing sword started to vibrate out of nowhere. So he was able to explain this because there was a fan in a nearby room that was causing infrasonic waves at 19 hertz, I believe. So just below the range of human hearing. So the point is that he couldn't hear the sound, but there were sound waves and they were affecting him somehow. Maybe the vibrations were causing his eye to vibrate, and this was causing him to see things out of the corner of his eye. Again, I can't really verify this myself, but I thought it was interesting in any case. And the third type of sound wave are those that have frequencies above the audible range. These are called ultrasonic waves. Ultrasound, of course, is used a lot in medicine, particularly for imaging with ultrasound machines. Cats and dogs are sensitive to sounds in this range. Cats can hear sounds up to 64,000 hertz, dogs 45,000. Dog whistles emit sounds between 23 and 54,000 hertz. That's why dogs can hear them, but we cannot. It's above our range of hearing. And also, if you have a cat and he's kind of jumpy out of nowhere, maybe this is why. Maybe because he can hear things that you can't. And then, of course, bats and insects can also use ultrasound to maneuver, right? Bats send out sounds, they echo back, and that's how they can navigate through dark caves and things like that. The speed which sound can propagate through a fluid depends on two properties of the fluid. So the speed v is equal to the square root of capital B over rho. Capital B is called the bulk modulus, and this measures how much a substance is incompressible. So air, for instance, has a relatively low bulk modulus at 142 kilopascals, Water is relatively high at 2.2 gigapascals, and steel is even higher at 160 GPa. So this tells us that air is fairly compressible while steel is very much not compressible. Rho is the density of the substance. And from this formula, you can actually see that if a substance is more incompressible, then it will have a higher velocity. Since b is in the numerator, a larger b will result in a larger velocity. So water, for instance, has a higher incompressibility than air, so the speed of sound in water is significantly higher than the speed of sound in air. In chapter 13, we learned about the speed of sound on a string. We found that v was equal to the square root of the tension in the string divided by the linear mass density of the string. And these formulas are actually very similar. The bulk modulus is related to the incompressibility of a substance, and the tension is how tightly you're pulling the string. And then, of course, in the denominators, the density is very much similar to the linear mass density. Now at the bottom here, we have a formula for the speed of sound in air. V is equal to 331 times the square root of T over 273 Kelvin. This T is the air temp, and it has to be in units of Kelvin. But this formula gives you a rough estimate of how fast sound is traveling through air. And I realize that the formula at the bottom does not match up with the formula at the top, but the note that I have at the bottom says that we should consider this a special case of the equation that's shown at the top, rather than a contradiction to it. This formula at the bottom does not apply to all fluids. So, question, if sound travels at 343 meters per second in air, and humans can hear sounds between 20 and 20,000 hertz, what are the range of wavelengths that we can hear? Unpause it when you're ready. Okay, since sound is a wave, the formula V is equal to lambda F applies. In this question, we know what the speed of sound is, and we know what frequencies we're interested in. So we solve for lambda. Lambda is equal to V divided by F, and then we just plug in the numbers that were given. If you plug in 20, you will find that lambda is equal to 343 meters per second divided by 20 hertz, and you'll find 17 meters. If you plug in the high range of frequencies, you'll get 20,000 hertz and 0.017 meters. So this tells us that humans can hear sounds that have wavelengths between 0.017 meters and 17 meters. And this is actually a huge range for sounds that we can hear. Right at the low end, we can hear sounds that are 1.7 centimeters wavelength, which is relatively small. And then at the high end, we can hear sounds that are 17 meters in wavelength, which is very large. It's maybe a very large room. Now these next few slides are related to standing waves, which is something that we did in the lab. So if you haven't seen the lab video yet, please watch that because I explain it in quite a bit of detail. Here though, recall that when waves overlap, they combine via superposition. So if you have two waves like these that I'm pointing to, since they're overlapping exactly, they'll combine to create larger peaks and deeper valleys. On the other hand, if you have two waves that are sort of anti-overlapping, like shown on the right, when you combine these via superposition, they will give you just a flat line. You can combine these two effects by letting two traveling waves pass by each other, one to the left and one to the right. In the GIF at the bottom, you have a red wave going left and a blue wave going right. And as they combine, they create this black wave that does not look like it's moving at all. This is called a standing wave. And actually, let me just remind you of one more thing. The waves that overlap, such as on the left, these are called in phase. And when they anti-overlap, we say that they're 180 degrees out of phase. Nodes, as we talked about, are points on the string that do not move, points on the standing wave that do not move. So in the GIF at the bottom, these are the red points. All the other points look like they're going up and down, but those red points very specifically do not look like they're moving up and down at all. Antinodes are the points on the string that oscillate the most. So the antinodes are in between the nodes. So notice that the distance between two adjacent nodes is half a wavelength. Let me just draw a wave here. So here I've drawn a full wavelength of this wave shown at the bottom. The distance between two of the red points is 1/2 of the full wavelength. So we would say that the distance d between two nodes, n, is equal to 1/2 times lambda. Notice also that the distance between a node and any adjacent antinode is 1/4 of a wavelength. So if one wavelength is what I've drawn at the bottom, then 1/4 of the wavelength is this distance right here. So that's the distance between any node and the adjacent antinode. So now suppose that we fix a string so that it's attached to a wall on both ends. And then suppose that we pluck the center of that string. We'll be in the situation shown at the top in the first picture. The two ends do not move at all because they're fixed to the wall. So these points must be nodes. The formula from the previous slide was dnn is equal to 1/2 times the wavelength. We can solve for lambda there to get lambda is equal to 2 times dnn. And we're actually going to label this as lambda 1 because it has one antinode in the center. This distance must be 2L. This is something that I explained in the lab video, so I won't go over it again. But this formula at the bottom I do not think we've seen before, so let's go over that. We have V is equal to lambda F. If we want to find the frequency for this wave at the top, we can solve for F. So we get F is equal to V over lambda. Lambda we just found was equal to 2 times the length of the string. And for V, we can plug in the formula for the wave speed on a string. And that's how we get those equations at the bottom. Now this particular arrangement of standing wave we call the fundamental frequency for this string. This is the first harmonic for that standing wave. That is why we put little sub 1s next to lambda and F. The second harmonic happens when there's an additional node in the center of the string. So that's going to put us in the center picture here, and we have an extra node at the center. The wavelength of the second harmonic is L, the length of the string. We can get this from the formula as well. So if you have lambda is equal to 2 times the distance from one node to the next node, and then you look in the center picture, you can see that the distance from one node to the next node is 1/2 the wavelength, or I'm sorry, 1/2 the length of the string. So then you have lambda is equal to 2 times 1/2 L, and the wavelength of the second harmonic is the length of the string, L. The frequency we can find similarly. You have V is equal to lambda f, then you plug in L for the wavelength lambda 2, and then I actually want to rewrite this. So I have V over L. I'm going to multiply by 2 and divide by 2. So those 2's will cancel each other out. But the reason I write it like this is because the quantity in parentheses here, this is equal to the fundamental frequency from the previous slide. So let me just flash back and show you that. You have F1 is equal to V divided by 2L. So then if I go back to this slide, I have the frequency of the second harmonic is equal to 2 times the frequency of the first harmonic. So F2 is equal to 2 times F1. So then on this slide, we have determined that the wavelength of the second harmonic is 1/2 as long as the wavelength of the first harmonic, but the string is vibrating twice as fast with twice the frequency. For the third harmonic, we want to add another node between the two walls. So then we have 2 nodes between the walls, as well as the 2 nodes on the walls. This puts us in the bottom picture. The wavelength and the frequency equations are derived in the very similar way as we did with the second harmonic, so I'll leave those to you, but let me point out the pattern. For lambda 1, we had a wavelength of 2L. For lambda 2, we had a wavelength of 2L divided by 2. For lambda 3, we have a wavelength of 2L divided by 3. So hopefully you can see the pattern that's developing here. In general, for the nth harmonic, for a string that's fixed at 2 ends, the wavelength will be 2L divided by n. The frequency has an even simpler pattern. The frequency for the fundamental, or for the first harmonic, was just F1. For the second harmonic, it was 2 times F1. For the third harmonic, it was 3 times F1. And of course, the pattern here is just n times F1 for the nth harmonic. These two equations are what we call the harmonic series for this string. In the lab prep video, we also called this n the mode number for that string. And we saw that it was equal to the number of antinodes. So in the top picture, we have 1 antinode, so n was equal to 1. In the middle picture, you have 2 antinodes, and in the bottom picture, you have 3 antinodes. In this question, we have a standing wave on a string. If the total length of the string is 5 meters, what is the wavelength of this standing wave? Unpause when you're ready. There are a few ways you can do this, but let's use the equations from the previous slides. So this is a standing wave with 1, 2, 3, 4, 5 antinodes. That means the mode number for this standing wave is 5, or it's the 5th harmonic. The wavelength then, lambda 5, will be given as 2 times L divided by 5. If the total length of the string is 5 meters, we would do 2 over 5 times 5, which would give us 2 meters. If you trace out one wavelength, you'll see that it looks like that. And this hopefully matches up with what you were thinking as well. So the answer here is B. In this question, we start with a string that has a fundamental frequency of 150 hertz, and I ask which of the following frequencies are allowed to be frequencies for the higher harmonics of that string. It's maybe a little confusing to think about which frequencies are allowed, but do think about it for a little bit and then unpause when you're ready. So the fundamental frequency is determined by a few properties of the string. We had this formula 1 over 2L times tau over mu. The length of the string, the tension in the string, and the linear mass density of the string are all properties of the string. So the fundamental frequency is determined by the string itself. The higher harmonics have frequencies determined by the fundamental frequency. In fact, they're all just multiples of the fundamental frequency. So the numbers that we're looking for in the answer have to be multiples of that 150 hertz. Of the numbers shown, only 300 and 600 are multiples of 150. So the answer is B and E. Answer B is 2 times the 150, so this corresponds to the second harmonic, and 600 is 4 times 150, so answer E corresponds to the fourth harmonic. In this problem, we start with the standing wave at the top that has a mode number of 2. Then we reduce the tension in the string to 1/4 its original value, but we keep the frequency and the length of the string the same. So the question is, which of the patterns at the bottom is the result? Unpause it when you're ready. So one way to answer this question is to look at the wavelengths of the waves in all the different pictures. If we want to do it this way, we need some way to relate wavelength to the tension, because the tension is what we're changing. So if we start with the equation V is equal to lambda times F, and we plug in the square root of tau over mu for the speed of the wave on the string, this will be equal to lambda times F. Now in this equation, mu and F are not changing because the string is not changing, so mu is the same, and the problem states that the frequency is not changing. So now on the left, if we reduce tau by a factor of 1/4, that 1/4 is inside of a square root. So maybe I can write it like this. You have the square root of tau goes to the square root of 1/4 tau, and this is going to be equal to 1/2 times that square root of tau. So if we reduce tau by 1/4, the left side of this equation, in the middle, reduces by 1/2. To compensate for that, the right side of the equation also has to reduce by 1/2. So if tau reduces by 1/4, then lambda has to reduce by 1/2. In the top picture, the wavelength of the string was equal to the distance between the walls. So the wave that we're looking for in the bottom pictures has to have half that wavelength. The only one that corresponds to that wavelength is picture C, where the wavelength of the standing wave is half the distance between the two walls. So the answer is C. You may have guessed this, but harmonics are named as such because of their relationship to music. So when we talk about harmonics on a string, you can relate that to stringed instruments. And here we're going to be talking about standing waves in tubes. So here you can relate harmonics to, say, a pipe organ. So suppose we strike a tuning fork and we put it at the end of one of these tubes. That tuning fork is going to send a sound wave down the tube. That sound wave is going to reflect off the back of the tube, and it's going to come back out the left end of the tube. Now notice here that I'm drawing the sound waves as transverse waves, but remember that we had this comparison between transverse waves and longitudinal waves. And remember that sound is a longitudinal wave. So at the right end of the tube, the molecules are prevented from vibrating. You have molecules all the way up against this wall, and they cannot vibrate because they have a wall next to them, and the wall is not moving. Since those molecules are not moving, the closed end of the tube has to be a node. At the open end of the tube, we can form an antinode if the sound has the right wavelength. The first harmonic will be as pictured, so that there's a node at the right end of the tube and an antinode at the open end. To find the wavelength of this wave, let's trace out the wave, one repeating pattern. So we start at the center, we go up to the top, we go back down to the center, we go to the bottom, and then we go back up to where we started. So then the length of the tube is 1/4 the total wavelength. So we can write L is equal to 1/4 times the wavelength, or lambda 1 is equal to 4 times L. Another way we can determine this is to use the distance between the node and the adjacent antinode. This is equal to 1/4 of the wavelength, which we saw from one of the earlier slides. To then determine the frequency of the first harmonic, we can plug in F is equal to V over lambda, and then lambda is equal to 4 times L. To determine the next harmonic, we want to repeat the procedure that we did with the string. We added another node, and this also added another antinode. So this will bring us to the second picture, where we have an additional node and an additional antinode inside of the tube. Now, the wavelength of this harmonic we can fairly easily determine using the distance from the node to antinode formula. So to find the distance from a node to an antinode, notice that there are 3 node-antinode sections. That means the distance from the node to the adjacent antinode is 1/3 the entire length of the tube. So then we plug in 1/3L on the left side, and we have 1/4 lambda on the right side. And this leads us to the equation for the wavelength is 4/3 times L. We can find the frequency of this harmonic similar to how we did on the previous slide, and we'll find that the frequency of this harmonic is 3 times the frequency of the first harmonic. So I skipped some steps here, but if we develop the next harmonic by adding one additional node-antinode pair, then this last equation actually shows us that the next harmonic is the third harmonic, and there is in fact no second harmonic for this open-ended tube. If we keep working our way up the harmonics by adding node and antinode pairs, then we will find that for a pipe that is closed on one end, there are no even harmonics at all. We'll also find that the pattern for the odd harmonics is that the wavelength of the nth harmonic is 4 times the length of the tube over n, and the frequency is n times the fundamental frequency. So here's kind of the point of these last few slides. If you have a closed tube of fixed length and you play a sound near the open end of the tube, then you will have an antinode near the end of the tube if the frequency matches up with one of the harmonic frequencies. This is important because the antinode is where the amplitude of the standing wave is the largest. When you have a sound with a larger amplitude, it will sound louder to you. This is something that we call resonance, and we will talk more about it next time. So that's all I have for lecture today. Now, in place of discussion, I would like you to go over example 14.10 in the textbook. This example is similar to what we were talking about in the previous few slides, But if I give you a rundown of those slides, I would say that we started with a fixed length for the tube, and we determined which frequencies would be the loudest at the end of the tube. So which sounds would resonate at the end of the tube. This example flips it up a bit. So you start with a fixed frequency at the end of the tube. You start with a tuning fork that has a fixed frequency. And then you adjust the length of the tube by moving it up and down in the water. So then the length of the tube will be from the open end to where the water starts. So on the previous few slides, the known variables were the speed of sound and the length of the tube. This allowed us to calculate the first harmonic, or the fundamental frequency, with this equation. And in this example, the known variables will be the length of the tube, which you know because you're adjusting the length of the tube, and also you will know the speed of sound in air. So knowing these things, you can determine what the frequency of the tuning fork will be. And I also really want you to go over this example because it's very much related to the lab that we'll be doing next week. And that's all I have for you today. So let me know if you have any questions, and have a good one.